This is a brief introduction to electromagnetic radiation, which can be abbreviated EMR. Let's organize it with a flowchart. And as always, if you need more time to write down the information, pause the video. We'll start by listing the types of electromagnetic radiation. Visible light is the type that we're most familiar with because that's what our eyes evolved to detect. And it's the only EMR we can see without special equipment. Visible light is comprised of all the colors of the rainbow: red, orange, yellow, green, blue, and violet. The EMR above visible light have higher energy, and exposure can damage the DNA in our cells. That's why it's important to protect our skin from UVA and UVB rays from the sun by wearing a full spectrum sunscreen. Above that is X-rays, which we don't usually get many times a year. We only get X-rays when the benefit of a diagnosis outweighs the risk X-rays pose to our health. And the highest EMR is gamma rays, which occur naturally in phenomena like radioactive decay of some elements. Some are useful in radiotherapy when their energy is targeted at tumors to kill cancer cells. Infrared energy, which measures temperature, falls below visible light and can be detected with night vision goggles. Below that is microwaves, which not only cook our food, but are also used by our cell phones to transmit text messages and information. And microwaves are what Wilson and Penzias detected as that faint microwave signature from space that they used as evidence for the Big Bang Theory, that moment in time when all the matter that would ever exist was created. Below that is radar, used in air traffic control, and speed traps to catch motorists driving too fast on the highways. And the lowest energy EMR is radio waves that can be sent out over the airwaves and picked up by radios in our homes and cars. All of these radiations travel at the exact same speed, which is the speed of light. Because all these radiations are considered light, they're just different forms of light. All these radiations will travel at 3.0 times 10 to the 8 meters per second, or 300 million meters per second. At that speed, you could travel around the Earth 7.5 times in 1 second. The speed of light was given the variable c for celeritas, a Latin word meaning swiftness, and it has to do with the fact that light travels so quickly. Speed of light is the product of wavelength of EMR by its frequency. Wavelength is symbolized by the Greek letter lambda, which looks like an upside-down Y, and frequency is symbolized by the Greek letter nu, which looks similar to our letter V. If we're talking about EMR, their product will always be 3.0 times 10 to the 8 meters per second. So the formula for speed of light is lambda times nu, or wavelength times frequency. If you need practice using this formula, be sure to view my EMR calculations video on finding wavelength and frequency. So what is a wavelength? It's the distance from crest to crest or trough to trough in a wave. A crest would be the highest point in the wave, and a trough would be the lowest point. The frequency relates to how frequently we see the wave, and it's measured as the number of waves that pass a point in a given time. The unit is waves per second, which is also called a hertz. This unit is named after a person, Heinrich Hertz, so it starts with a capital H. Let's label the parts of a wave. As stated earlier, a crest is the highest point of the wave, and a trough is the lowest point. The distance from one crest to the next is a wavelength, which is also the same as the distance from one trough to the next. The amplitude is a measure of how high the wave rises and is measured from the midline to the highest point. Here is the whole electromagnetic spectrum. Gamma rays are on the far right, and we can see there's very little space between the crests, meaning it has a small wavelength. We can also see the value for wavelength is given as 10 to the negative 14, representing a small number, which is much lower than 1. Compare that with radio waves on the left with a wavelength value of 10 to the second, which represents 100, a number greater than 1. This shows us wavelength increases moving from right to left. The frequency of radio waves is 3 times 10 to the third, or 3,000, while the frequency of gamma rays is 3 times 10 to the 22nd, or 36 tillion. So frequency is increasing, moving from left to right. This relationship is going to be very important for us to understand and remember. As frequency increases, wavelength decreases, and vice versa. This is because the longer the wave, the less waves will be able to pass in a given time. The shorter the wave, the more waves will pass. We call this an inverse relationship when they do opposite of each other. We can show it in a graph with a downward slope. When the wavelength is high, the frequency is low, and when the wavelength is low, the frequency is high. Now let's determine the relationship between frequency and energy. If you remember, gamma rays have the highest energy and radio waves have the lowest. So we can see that energy increases going from left to right, same as frequency does. When two variables respond the same, we call that a direct relationship because they are directly proportional to each other. If we were to graph it, we can see that when energy is high, so is the frequency, and when the energy is low, the frequency is low as well. Let's add these relationships to our flow chart from earlier. Gamma and X-rays have high energy and high frequency, while radar and radio waves have low energy and low frequency. Wavelengths are reversed, with radar and radio waves having long or high wavelengths, and gamma and X-rays having short or low wavelengths. Keep this flowchart and notes in your binder and refer to them frequently when studying. Thank you so much for joining me today, and I will see you soon.